Okay, we're recording now. Share my screen, and we'll get started with class today. Quick announcements first. So reminder that the quiz that's in the folder here for week 12 due Monday, beginning of class. Again, you can use any resources that you want on that, and you should print it out and bring the printed out copy to class so that we can begin by grading it and going over it. We're gonna spend actually a lot of time talking about it because last time the class was taught, students tended to do pretty poorly on this section of the final, and the final exam will be like the quiz. And I also think it's some of the most, if not the most important material in the class. So I want us to do well on it. Other announcement is that in order to make sure that you have time to really focus on getting the quiz done and complete before Monday, then I've extended the programming homework deadline, the Twitter indexes deadline to be Wednesday. That's Wednesday at midnight. And because of the extension, there's no collaboration extension possible on that. Any questions about admin things? Okay, then where we left off last time, we had talked about everything that you needed for the homework assignment, the programming homework assignment. This time we're going to go just finishing up our discussion of some of these indexes and this operator, and there will be some of the material needed for the quiz that we didn't quite get to. In particular, looking at the quiz, everything before problem 7 is all related to just B trees or general non-index related things. So all that was covered prior to this week. Problems 8 and 9 related to full text search, and specifically with GIN indexes. Everything can be done with the GIN indexes on these ones. Problem 7, though, you'll explicitly have to use this RUM index for problem 7, and so we'll get to that today. So reminder, the GIN index, we're using it for full text search, indexing JSON, and we didn't talk about indexing arrays, but that's the other thing to use it for, and using any of these operators that contain the @ sign. The RUM index will be fixing some of the limitations of this GIN index, and so we'll real quickly talk about what these limitations are. So reminder about the way the index looks sort of physically. This is the picture to keep in your head about it, that we have a B tree, but the B tree is not on the actual text itself like it was for the B tree index. This B tree data structure is on the individual words in the text. But otherwise, it's very similar to the B tree. The structure up here, same as the B tree. And then down here in the leaf nodes, we're storing the tuple IDs of each document that contains whatever the individual word was. And then the documentation has some examples on doing the actual queries and how that works. One of the things that they mention in the document is that the GIN index is particularly slow doing its updates. And the reason for that is that in a B tree index, we're only ever going to be updating one, we're only ever inserting one word at a time, one item at a time. But in a gin index, if our document has lots of words in it, we're going to be modifying potentially up to every element in this B tree at once. So indexing or inserting is slow in the gin index. Another problem is that the gin index does not store this what's called auxiliary information. So if we had like a search engine that was, so like Google, the way they do their rankings is by page rank of the document, or also by timestamp. Google prefers ranking recent documents before older documents. None of that information is stored in the gin index at all. So position of lexemes means that if you wanted like the words United States to be directly next to each other, the gin index can't do that. And so if you're trying to do these sorts of things, you'll have to recheck the actual heap pages in the table and things will be slower. So the RUM index is going to fix these limitations. Another limitation is does not support the index scan or index only scan, only supports the bitmap scan. The main implication of this is that limit operations are not efficient. So coming back over to our problem 7 over here, we have a text search query, this at right here, and there's this limit clause down here. And so that's a sign that you can't use a gin index to make this query efficient. So the problem doesn't actually use the word RUM index anywhere, but because there's a limit clause right here, and it's asking you to take advantage of that limit clause, you'll have to use a RUM index for this problem. Can't use a gin index. Similarly, this order by, because it's a bitmap scan, a bitmap scan can't return things in sorted order, so you can't use this order by clause right here either. Yeah, so there's the does not sort the results. And we haven't explicitly talked about the cluster command, but you are responsible for that on the final exam, and the gin index does not support that. But no, actually no full text index would support this. Really only the B tree supports this. So the RUM index fixes most of these limitations of the gin index, and we'll talk about why that is the case today. Before I do that though, the main limitation of the RUM index is it's not built into Postgres. So over here is the Git repository for the RUM index. And if you wanted to use this in one of your projects, which it's sort of like the standard for full text search in Postgres at this point, then it's not built into Postgres like the gin index is. You have to clone the repo and follow these installation instructions. So it's a little bit more awkward to use. So the picture, this documentation here, or this picture is from the documentation for the RUM index. And this picture is essentially the same as this one over here for the gin index. But what they're trying to illustrate now is that in the B tree itself, in the leaf nodes down here that contain the actual information, it's not just tuple IDs that are stored with each of these words. Instead, there's this gray box here which represents some sort of auxiliary information. And this auxiliary information can be arbitrary amounts of information. Just like in a multi-column B tree index, we could have arbitrary extra columns attached to it. In the RUM index, we can add arbitrary amounts of information right here. So what the default information that's added is actually the position of each of these words in the document. So here, the black 1, 2, that's the tuple ID that contains the document good. This 7 right here is the word good is the 7th word in this particular document. And so by storing these word positions, you can make sure that 2 words are actually next to each other in the document. But you could also store, like we said before, things like the page rank of a document or the timestamp that the document was created, other things that are useful for making your full text search engine actually return more valuable results. On this documentation page here, I'm going to go through their subsequent examples just to highlight the things that are going to be particularly important for completing this, this quiz problem right here, number 7. So in their example, so after they get done with this toy example up here, this toy example is again the same example from the GIN index. They're creating a real sort of database for text search of this PG-SQL hackers mailing list. This is the mailing list for all the developers of Postgres, and it's a common data set for people to use to just test things out on Postgres databases. And so it's a bunch of emails, and they're just inserting those emails into this table right here. And we're gonna first create a couple of GIN indexes on that table, see what the query plans look like down here, and then compare those to the query plans for the RUM index, and we'll see why the RUM index is going to be faster. So again, the key thing to remember about syntax-wise for creating indexes that are not B-tree indexes, you have the table name, then the using, the type of the index, and then the columns that you're indexing. So that's how we know this is a GIN index right here. And then they're doing a full text search query right here. So TSV is, in our full text search queries, what we were doing is I was manually putting the to TS vector call inside of the where clause. In their queries, they are storing the TS vector directly inside of the database. And so this right here, TSV, is actually the TS vector. And then here is their query. This syntax right here of the sort of less than dash greater than sign, there's a dash in the middle here, not an underscore. This is trying to indicate that the word hello and hackers come right next to each other inside of an email message. So this would be probably looking for email messages that start with the words hello hackers at the top, although that could appear anywhere in the message. And we've said before that the GIN index, so we're using a GIN index, it only supports the bitmap scan. And so this is what the query plan ends up looking like. That the index, bitmap index scan portion right here, again, just taking the TIDs from the GIN index. And this bitmap index scan is not capable of doing this operator right here, because again, this operator right here needs to know the positions of these two words in the document. So because of that, we have this recheck condition up here, where down here, it's going to get all the documents that have both the word hello and hackers anywhere in them, and then the recheck condition is going to filter those after we've actually touched the heap table to get the documents that only have hello and hackers in them. So here, the index scan, 1,700 rows, removed by the recheck, the vast majority of them, touching a lot of heap blocks here, 1,500 heap blocks, because we're just getting too many tuple IDs returned by this index scan right here. The query itself still, I mean, reasonably fast, 18 milliseconds. So it's a relatively small data set, only 300,000 or so messages in it. So that's why it's still reasonably fast. But if you were Google or something trying to index the whole web or index all of tweets, then this would not be what you'd want to do, because it's not going to be efficient for that type of scale. Any questions about what the GIN index is doing here, or the setup of the problem, before we talk about how the RUM index is going to fix this? Sure.
So when it does its recheck and it's finding documents that have both hello and hackers in the same document for the same tuple ID, it's not guaranteeing that they're right next to each other, though?
At this point right here, it's not guaranteeing that they're right next to each other. That all that the index scan is capable of doing is doing hello and hackers. So it says hello, this funky sign hackers right here, because that's what is in the actual thing that we typed in. But what it's actually implementing is the hello and hackers, because that's all the gin index can do. And at this point right here is where it's checking to see that they're actually right next to each other. And so that's why, I mean, there's going to be a lot more documents that contain these two words anywhere in the document. So 1,700 of them. But then after we filter out that small subset so that it only has, that they're forced to be right next to each other, then that gives us 259. So this filtering step right here, this rechecking that condition is going to be necessary to get the correct results. Did that answer your question?
Yeah.
Any other questions about the setup of this problem at this point? Okay. I guess, yeah, so another one of these main takeaways is that if you're trying to use any sort of query where you care about the, not just the, what words are in the document, but what order those words in or their positions relative to each other, then this, you'll have to have this recheck condition step up here, and it's going to be expensive with the gin index. So the next thing to do is they delete the gin index and build the rum index. Again, just changing the word gin to rum right here does that. And they run this same query, and here's the results. So in this case, it is still a bitmap index scan. The rum index supports other scan types, but for various reasons, it's choosing to use the bitmap index scan here. But now you'll notice that this condition right here, hello, and then the arrow hackers, the number of rows returned by that, 259, directly matches the number of rows in the heap scan. And so the number of heap blocks accessed, 250, significantly smaller than up here. For the gin index, accessing the full 1,700 here, because it's only able to do the check of an and right here. And then accessing 1,500 heap blocks. Technically, there are some instances where you might have to actually recheck the condition here. This is due to memory limits on how many tuple IDs this can return down here. If the number of tuple IDs is so large, it won't remember all of the tuple IDs, it'll just remember the page IDs. And so that's why this is still listed here, because it's something that it might have to do. That's true for anytime you have a bitmap index and a bitmap heap scan, the recheck condition will always be listed here. And again, the documentation or the reference on the bitmap scans will explain why. But this operation is actually not going to be performed in this case. And so you see there, it just goes straight from the heap blocks up to the recheck condition down here, whereas up here it goes from the heap blocks, tells us that it actually performed the recheck, removing 1,500 rows, and then does the recheck itself. So this line right here is how we actually know that the recheck happened. So it is a little bit confusing that this line exists in the query plan, but there's actually nothing to recheck, and this line doesn't happen in the gin index. So that's the first way that the gin index, better than the rum index, supporting this this operator right here, making our bitmap scans faster, more efficient. Any questions about that? Okay, the next is whenever you have sorting by relevance, or so in particular an order by clause. And So the order by clause here, this operator is a little bit different than the operator that we saw above in two ways. First, this operator is sitting outside of the TS vector TS query syntax. So this is actually an operator directly in Postgres and not an operator in the TS query syntax. So here, this little arrow operator inside the quotation marks. So it's part of the TS query syntax. This operator outside of quotation marks, so it's not part of the TS query syntax. There's a typo up here in their code. This and GTL is supposed to be a greater than sign. They just, when they were reaching for the semicolon, which is supposed to be what's right here, they hit the L instead, and so that's why it says that instead of that, but it's supposed to be the same thing. The other difference typographically is that this is an equal sign instead of a dash sign like we had up here. So it's easy to confuse this operator and this operator, but totally different things. And what this operator down here is doing is it is giving us a relevance score. Exactly how this relevance score is computed is beyond the scope of our class. This would be something that in the data mining class I'll be teaching next semester. We'll talk about that a little bit. But it determines just based on these words over here, like how important this query is to this document. And in this case, higher numbers are better. And so it thinks that the word slit is a little bit better match over here. Presumably because slit is a less common word than sheet. And so it's more informative to your query. So anytime we have an order by clause in our, where there's also a where clause that's doing a full text search, there's many things that we can order by. So this up here is one of them. This TS rank is another one. Do very, very similar things, but there's a handful of different things that you can do this ranking by. In the, this question over here, it's using the this symbol right here, but there are other symbols that could appear on your final exam. And then here we're also actually doing the a limit as well. Question?
Yeah. What other symbol can we expect? Because I just feel like the documentation.
The question is, what other symbols can you expect? And the answer is anything that is on this GitHub page. So you're responsible for, if you see a symbol and you don't know what it is, looking up in the documentation, either if it's rum in particular on this rum page, or in the Postgres documentation. So here's some other common ones, but again, these are only the common ones. We have to go through the whole documentation to see them all. Good question. Any other questions?
Professor, I think I have a follow-up question.
Go ahead.
I was just wondering if we have that, like, do we really have to understand what is going on, or we just need to create an index for it?
Question is, do you really have to understand what is going on, or do you have to just be able to create an index for it? And the answer is that, so the way that you're going to be tested on it is just, can you create an index for something? But in order to know like whether you can create the index or know how to create the index, really the best way to do that is to understand what's actually going on. There will also be that section of true and false questions that will test a little bit more internally about like what's going on under the hood. But ultimately, if you're able to write the optimal indexes for particular queries, then you are, that should be your ultimate goal.
Can we have an example of that? Because I feel like sometimes it's just like hard to maybe using that symbol. of like using that symbol to create an index?
Yeah, so we're going over that now.
Okay.
Yeah, so the question is, how can I create an index that's going to speed up these symbols right here? And so we already have the GIN index that we created up above. And here they're going to talk about using, again, that GIN index, what the query plan is going to look like. Again, the GIN index only supports the bitmap index scan. That the bitmap scan does not support returning things in a sorted order, and it does not support returning things one tuple at a time. You have to return all of the tuples at once. And so after these, the bitmap index scan, the bitmap heap scan to combine those tuples together, we have this explicit sort right here, and followed by a limit clause. So these two things are going to be the particularly expensive operations, because maybe our documents, like we could have an arbitrary number of things that match this condition right here, maybe millions or billions of them. We only care about the first 10 though. So that would be very typical of a query that like Google would use in their search engine. You have just the top 10 pages that they're showing for whatever your query term is. And they don't want to like actually return all billion documents that match this and sort all billion of those documents. You want to actually only do that on the top 10 documents. So the GIN index does not support that, so not efficient if you see a limit clause or an order by clause where the order by references anything related to TS queries or TS vectors. Using the GIN index, so again, same query right down here, but a much nicer looking query plan. We have an index scan instead of a bitmap scan. And then it shows our the index condition right here, and that it's going to be actually ordering the results for us down here. And so there's no explicit sort, no, yeah, and we don't have to actually examine everything in the index. We can only examine the important ones. And so execution time reduced by a factor of 6 in this case. That's because it's only a small data set of 400,000 documents. Let's see. So in this case, the ordering by and the conditions up here, this query right here looks very similar to this query right here, except for this and condition right here. If we didn't have this and condition right here, then the rum index that we've seen so far would basically work perfectly for this query. There, you would just have to adjust it for the right table names. But because we have that and, we would not be able to do the index scan by itself, because the index scan would not be able to do this information right here, because this created at is not actually stored in the table, in the index anywhere. It would have to touch the table in order to compute that. So this additional information, we mentioned that the RUM, one of the other main benefit of the RUM is that it stores that additional information inside of the index itself. And the notation for doing that is pretty awkward. So it's not, with the B tree, if we wanted to store multiple pieces of information, we just had over here in our list of columns what we were going to store there. In this case, though, in order to store multiple columns here, so this sent is what they're ordering by instead of the TS vector, so ordering by the timestamp. That's the key thing, that because we're not ordering by the thing that we're doing the condition on right here, we're ordering by something else. We need to do this sort of special syntax, adding that additional information, that sent column, the timestamp column, into the table. So that's what this sent column is right here. And it turns out there's multiple different ways of adding this column into the RUM index that would have different performance implications. In order to speed up the actual, like an order by or a where condition though, this is what you'll have to do. So whatever your TS vector column is, you add this, you specify that you want the add-on ops right here. And then the with clause allows you to specify options to the index that you're creating. All of the indexes allow different types of options, but this is the first time we've actually seen the syntax for that. And the attach sent corresponds to this column right here, says attach this column to TSV inside of this column. So if we go back up to the image, by doing that syntax, it'll put that extra information sort of in these gray boxes where it will have access to it after it's done the filtering, rather than putting it sort of inside the B tree itself. Doing that, then a query like this, we'll still get a very nice looking query plan where the ordering by, you can see the index condition on the full text search, but the order by on this operator on the sent column. Yeah, so again, the key way that you know you need to use this like extra syntax right here is because there's either something else in the where clause besides just this at, or you're ordering by something that is not directly related to the full text search, but in this case, the timestamp that it was sent at.
Professor, I have a question.
Yes.
So I was just wondering, what if we have like, I need to like really think about this question. All right. So for instance, wherever we have the with condition, like what if like in the order by it was where in the thing it was the same thing as order by TSV or something like that? Do we like maybe order by TSV like descendant or something like that? Do we have like to write TSV twice?
So the question is with this, the order by right here, we have, what if in the order by there was another condition based off of the TS vector somehow? The reason why you have to use the rum index with this extra syntax right here is because this is not related to the TS vector column. If this was related to the TS vector column, then you wouldn't need that extra syntax. You would still need a rum index because you would still need to do an index scan instead of a bitmap scan, and the GIN index does not support a bitmap scan.
I guess my question is just like for the create index, like do we have like, I know we not need the width, but like in the create index, like do we have like to specify maybe TSV and then TSV descendant or something like that? Like maybe we have
so in any type of index, you never have to specify the same column multiple times.
Okay. And do like the ascendant or descendant matter too? That was also one question I had.
Question is about ascending and descending. Does it matter? And the answer is yes. It is for any query that uses an index, whether you're ordering by ascending or descending can potentially change what type of index that you need to create. And I'm making you read the documentation to see how that affects things. And that's both for B-tree indexes and these GIN rum indexes.
I mean, the reason why I asked this question is just because of the documentation. Like there was like a part where like they were having the ascending and descending at the same time. And they were saying that you can put the—
I'm going to pause you for a second, and
okay.
Happy to answer this in more detail later.
Okay.
But I think now's not a good time for it.
All right.
Yeah, I want to make sure that we just finish up our discussion here of these indexes. Any other questions though about the rum index and the So again, takeaway is that if you have a limit or an order by, you'll want to use the rum instead of a gin. And if your order by uses any condition or your where clause uses any condition that is not based on the full text search, you'll need to use the that special rum syntax up here. Any questions about that?
Yeah, can I ask like this question? So what you mean is just like if in this case we remove the order by and have like maybe TSV at to TS query and an end, we still need to use the with. We can just like limit it to the using ROM and put those two columns inside it.
Anytime with one of these indexes, with a rum index, you want it to be multi-column, you're going to have to do something special like this. You'll never want a multi-column index that does not have something here and something here for a rum index.
But then like can we use multiple with, or we just limited to one with to write all
The question
the thing?
is, if you have more than one column being added, what's the syntax down here that you'd have to use? And the answer is you'll have to look at the documentation for that.
Okay.
I honestly don't even know off the top of my head. If I were doing that, I would have to look at the documentation. And even for something like this, I don't memorize this rum TS vector add-on ops and this stuff here. I'm always looking at the documentation in order to be able to do this.
Thank you.
Okay, so yeah, summary of the run index. So you're storing this extra meta information in the index. Return the results in sorted order, and in particular, you're able to use an index scan. Actually, sorry, this is a typo. You cannot use an index-only scan. You can only use an index scan or bitmap scan. Limitations, though. So when you're doing, we already talked about the gin index was slow for inserts and updates. The rum index is even slower for inserts and updates because there's more information that has to be stored. And it also uses a lot more disk space than the gin index because of all this extra meta information that's being stored. And so I want to look at this portion of the documentation right here where it's talking about the size of the different indexes. And so here, this is for that PG Hackers data set. The gin index here on that data set is pretty small, under 200 megabytes. Rum index on that data set, more than twice as large. The B tree index, what they're meaning by a B tree index is if you just stored all of the data, all of the documents directly inside of the B tree rather than putting them into the gin or the rum database. We'll see this gist index here next, and you can see that it has the smallest memory footprint of all of these index types. So if you're, these three index types all support full text search. B-tree does not. If you're really concerned about performance for the lookup times of full text search, then it's the rum that you want. But if you're more concerned about space issues or insert performance, then it's the gist index that you want. So this gist index, we're not going to cover it in super detail. The main takeaway, though, is that much faster inserts, but much slower lookups. And for most applications, fast lookups are much more important than fast inserts. So if you're like Twitter, Google, any company making a search engine for your product, then the actual like inserts is all happening on the back end. You just have to add more back end resources to make that go faster. But the lookup is happening right when the customer appears, and that's the time that you typically want things to be fastest. A lot of data like analysis applications though, so where you only have sort of one-off tasks that you're doing or more limited tasks. The main thing that I'm thinking about is like physics experiments at the Large Hadron Collider, something like that, where your customers are okay waiting more than a couple milliseconds for a query. but you have lots and lots of data that you need to insert, that would be a situation where the gist would be used. But otherwise, it's basically everybody's using the rum index for everything in full text search in Postgres. So back over onto the quiz. This problem 7 here again, using the rum index. 8 and 9 down here, you could use a rum index or gin indexes on those problems. Either way is fine. There's a slight typo that I have here in problem B that I want us to fix real quick. What this problem is asking up here in part A, I originally had said just create the fastest rum index possible, and but then I changed this the wording up here a little bit. So this question down here doesn't quite make sense as it's worded anymore. Part B is asking that if you are not able to create a rum index, what it should be asking is what indexes would you create instead? And so I've got an issue right here, problem 7B at the take-home quiz. This should be the alternative text that you should use to actually answer the question. So create alternative indexes that will speed up the query as much as possible if you're not able to make a rum index. And so the thing that you should be thinking about for that is make a gin index, and that'll do the full text search right here. You're not going to be able to speed up the order by in the limit clause in any way, but you still could speed up this other condition in the where clause with another index, a totally separate index on created at, and then a bitmap scan, which is again the only thing that the this condition or the gin index supports. The bitmap scan is the only thing that a gin index supports. The bitmap scan will be able to combine multiple indexes together to speed that up. So it won't be as good as a rum index, but it'll still be better than just a gin index by itself. So that's a hint for that second problem down here, both a gin index and a B-tree index. Yeah, question, Sally?
Yeah, so I was wondering, like, I'm kind of like sometimes I get confused about which index to use, like to actually get the index or like the bitmap scan. Do we have like a way of checking, like when we add, like for example, when we add specific indexes, if it's gonna be actually like using that, using the scan that we want? Like, is there a, some like data that we can play with for the quiz?
Yeah, that's a good question. So the question is, when we add, how do we check our work? Can we create indexes on here and run queries and see that it's actually going to take advantage of the indexes in the way that we want it to? And the answer is yes, you can check your work. These sets of tables up here are the same tables as the normalized database in the last Twitter homework assignments. The only difference is I've removed some of these columns just to take up less space on the page right here. So if you create the indexes on the Twitter assignment, then everything will carry over to what you're doing on the quiz. My recommendation is that you use the week 10 Twitter assignment, because that one has the smaller amount of data in it, so you can just create an index in a couple of seconds rather than waiting an hour or so for the index to create. But you can test out all of your queries and indexes on this assignment right here. Does that make sense?
Yeah, and like also, like if we do that, for example, and if we're also working on, week 10's data for week 12's homework,
Mm-hmm.
like would we have a collision of indexes, like, or would adding indexes for the homework affect it for the quiz?
Yeah, it's a good question. The question being, how will creating the indexes for the quiz interact with doing it for the homework assignment? And the answer is that they could. cause potential conflicts. And so my recommendation, again, when you're doing the creating the index for the homework assignment, one of the things that you're supposed to be doing is just putting them into a file somewhere. So my recommendation is to just like bring down the database, wipe the volumes, bring it up again, work on the quiz, trying out different indexes one at a time. And then when you're ready to go back to the homework, you have that file already existing that creates the indexes for you. And so you can rerun those commands quickly that way. Does that procedure make sense?
Yeah, thank you.
Good question. Any other
Professor,
questions
I just
about?
have a question.
Yes.
My question is gonna be like, I just noticed like something that confused me is just when do we have to like create 2 indexes instead of like 1? Because you
Question
just
is when to create 2 indexes instead of 1. So let's talk about the implications of multiple indexes versus a single index. So a lot of the problems say like create index with plural-ish thing over here, implying that you might have to create 0, 1, 2, or more indexes to complete the problem. Anytime, so some clues about times that you'll have to create multiple indexes are anytime you have join conditions, an index can only apply to one single table at a time. And so if you have join conditions, you will need multiple indexes, at least one for each of the different tables that you're joining on. So that's one time when you'll need multiple indexes. Anytime that I ask you, I specifically say the words index only scan or index scan. Anytime I say anything other than a bitmap scan, that implies exactly one index. Because the only scan strategy that supports multiple indexes is a bitmap scan. An index only scan and an index scan are both single index operations only. Very roughly, anytime you see something that has a simple condition like this, like there's a very simple problem, and I'm just asking you to make it as fast as possible. Anytime you see like make something as fast as possible, you're probably trying to aim for an index-only scan. You're going to have more sort of practice quizzes like this with harder problems, where eventually I'll ask you things like that on problems where an index-only scan is not possible. But at this point, if I'm asking you to make something as fast as possible and there's only one table in there, then you should be trying to do an index-only scan, which implies that you're only creating a single index. But again, here, you may or may not have to actually create that index because the index might already be created for you by the unique constraints up here.
Professor, also like something I like kind of like didn't figure out too was just like from the documentation was is the unique itself keyword like a unique constraint?
Unique is a keyword in SQL.
Yeah. Because like something I read yesterday was just like they were saying that unique itself like create an index already. So I don't know if we need to create an index for it.
So that's a true statement. So like here on problem 1, the key idea of this problem 1 is that the schema of the database is going to define certain indexes for you automatically. And the only thing that creates indexes for you automatically, at least that we're going to see in this class, is the unique constraint on a column. So here, this it tweets has a unique constraint on that column, so it's going to have an index created for it automatically.
Okay.
The two subtleties about that are that the references constraint will create, or it requires a unique constraint. So here, references on users, id users, requires that this id users column have a unique constraint on it. So every references will also be associated with an index somehow. The other subtlety is that recall that a primary key, anytime you see the word primary key, that's exactly equivalent to having unique and not null. There's no difference at all. So this id tweets right here is a primary key, even though it doesn't say primary key. And this id users up here does have a unique constraint, even though the word unique is not existing up here. So you have a unique index on id users and id tweets already created for you.
So we don't have to create them no more. That's what, like.
Exactly. So not only do you not have to create it, but you will lose points if you recreate it.
Okay.
Yeah, the questions down below ask things like, do not create any unneeded indexes. So if an index already exists that's going to make this faster, then don't create it. And
Because
in general,
I mean,
it's we don't want to be creating unnecessary indexes in our database, because that will cause us to it'll make our inserts and updates and deletes much slower. So we only want exactly the indexes we need and nothing else.
I mean, the reason why I'm asking that is just like, number one, said to list all the create index. I don't know if like it means to like why, if we like that's gonna be created automatically or not. So if you can bring a little clarification about that, that would be perfect.
So here we have a unique constraint right here on id tweets, and it's asking you to say to write out the index that's created by that. So create unique index on tweets, id tweets.
Oh, okay. All right, perfect.
So this is problem number 1 on the quiz, extremely similar to the notes from the week before. It's not exactly the same. The schema's slightly different. I've added some extra stuff here, but it's very similar. So looking at that as a reference should help.
Thank you.
Yep. Any other questions about quiz or anything else? Okay, then we'll end early. I have the office hours again today at 1 o'clock. You're welcome to come by and ask questions then. Otherwise, everybody have a good weekend and see you on Monday.